So in this video we will talk about what is electric field. So before going into electric field, let's first understand what is a field in general. Now field in mathematics or physics is just, suppose you have a three-dimensional space. Okay, this is your x-axis, this is your y-axis, this is your z-axis. Now this three-dimensional space is a set of points, right? Set of infinite points. Now if at every point I associate a number. For example, consider at the origin there is a heater. Okay, there is a heater which is heating continuously, getting hot. So this will have some temperature around it. Temperature will be maximum here, then it will reduce here, and then it will reduce further. So at every point in space, temperature has some value. So we say that temperature, this region has a temperature field. So field is nothing but a function of space time. I mean, it could vary with time as well. Suppose it is getting hot and hot, then at some point, say this point is 2, 1, 3, this point temperature may vary with time. So field in general can be some function of space x, y, z and time. So this is the concept of field in general. Now there are two types of field. One is scalar field that we have just seen. Scalar fields, and the other scalar fields is temperature field, right? At every point you just associate a number, scalar number. Other is the vector field. Now with the definition of scalar field, this vector field is obvious. We again have three-dimensional space, and at every point we associate a vector, which means it has some value, say 2 something, and a direction, some a cap, right? So if every point we associate a vector, then we will have a vector field. So this vector field will also be a function of space time. So consider f, x, y, z, and maybe time as well, right? So now we will go to the electric field. So what is electric field? If I talk about the definition of electric field at any point is a force felt by unit charge plus q, unit positive charge, assumed to be kept at that point. For example, if this is our system, partition system xyz, this is the origin. We want to know what is the electric field of this charge. This charge is capital Q sitting at origin. What is the electric field of this charge at some point r? Okay, r. So we place at r a positive unit charge of +1. So take this Q as +1. This is imaginary charge. I mean, we are just putting it. So to calculate electric field, why +1? It's just a convention. I will get back to it. So this force is some constant, 1/4πε0. Let's write it K times Q into Q, and this is 1. So this will become Q only. Q divided by 4πε0. Okay, 4πε0 is Q, r square, r cap. So this is a vector. So at every r, so this vector is a function of r. At every r, we have some value and direction. So electric field is a vector field. Okay. We can manipulate this formula, since r cap is r vector by mod r, and mod r is just r. So force because of plus q charge I mean, this is not force. This is an electric field because we have considered plus 1 unit charge here. So electric field due to plus q charge is k q r by r cube. Now you might think that electric force just behaves like a Newton's laws of motion, right? Electric force is proportional to 1 by r square, but here is a 1 by r cube, but it's not. It just looks like, because I have mapped equation like this. I have written the equation like this. R cap is written as r by mod r. So 1 mod r is coming from the unit direction. If you write it in this form, it is still inverse square law. So with that, let's do one simple example. Consider a 2-dimensional space. This is x, this is y, and at origin we have an electron 0 0. Now we want to calculate at some point p 2, 1 what is electric field due to electron at 2, 1. Okay, so we will use the formula. Formula is electric field due to electron is 1 by 4 pi epsilon naught q by r cube, and r here, q is electron charge, which is minus 1.6 into 10 raised to minus 19 coulomb, and r is what, 2 I cap plus j cap, and mod r is what, 4 plus 1 is 5, square root of 5. So just substitute, and the value of this constant is 9 into 10 raised to 9. So you can remember it, it's very useful. So capital Q is minus 1.6 into 10 raised to minus 19. R is 2I cap plus j cap divided by r cube, which is 5 raised to 3 by 2. So this is simply 1.44 into 10 raised to minus 9 divided by 5 root 5 minus 2I cap minus j cap. So this is the electric field due to electron at origin at some point p 2, 1. Okay. So calculating electric field because of discrete charges are very simple. If there are many charges, suppose one electron is here and another electron is at 0, 2, right? So due to both these electrons, you can calculate the electric field at point P by simply using superposition principle. So electric field because of discrete charges, calculating that is relatively simple. Now in next video, what we will do is we will calculate electric field due to, say, a continuous charge. Suppose we have one-dimensional charge. I mean, we have a line of charge, continuous line of charge. There the concept of charge density is important. In one dimension, charge density is total charge divided by length, which is it is spread into. Suppose this length is L, and at every point there is some charge, and the total charge is Q. So this Q by L is lambda. This is called linear charge density. Linear charge density. And in 2 dimensions, say we have a sheet of charges, and this is not discrete charge, this is a continuous charge. It is a sheet of charge. Suppose the total charge again is Q, spread uniformly. Then in this 2 dimension, we have surface charge density. Surface charge density. And this will be total charge divided by total area. And similarly, we have some 3-dimensional volume and plus Q charge spread uniformly in this volume. Then in 3 dimension also we have volume charge density. Again, total charge divided by total volume it occupies. So these concepts of this is represented as rho, right? The representation is pretty general. So this is rho, this is sigma, this is lambda. So we will use this concept in the coming video. Thank you, and if you want more content like this, do subscribe.